For centuries, we thought our solar system was a closed community. But a new class of visitor is changing that. Interstellar objects, rare travelers from distant star systems. We've only ever confirmed 3. The latest, 3I Atlas, is teaching us that every data point is precious. So what did NASA learn from this faint, fleeting visitor? And what mysteries are left to be solved? One thing is certain. Our solar system is a more dynamic place than we ever imagined. One fact to start: in over 4 billion years of solar system history, humans have only confirmed 3 objects arriving from interstellar space. Just 3. The latest is called 3I Atlas, discovered in 2019. Its trajectory and speed confirm it's not bound to our sun. That makes every data point precious, because it's a rare glimpse of material shaped around another star. What has NASA gathered about it so far? That's what we're explaining today, from its motion through space to the limits of what telescopes could track. The rarity of interstellar visitors. Why do astronomers call each interstellar object almost once-in-a-lifetime evidence? The reason is not the excitement of discovery alone, but the extreme rarity of the visitors themselves. Our solar system has been orbiting the Milky Way for more than 4 billion years, yet scientists have only confirmed 3 bodies that entered from beyond the sun's gravitational influence. When you set that against the countless comets and asteroids created inside our own system, the contrast is sharp. We regularly track thousands of objects that formed around the sun, but nearly none that traveled here from another star. The first hints of this changed in 2017 with ʻOumuamua, a fast, elongated object that confounded telescopes because it showed no obvious comet tail, even though its motion suggested some kind of gentle outgassing. Just 2 years later came 2I/Borisov, which behaved much more like a classic comet. It released gas and dust in a way that could be measured through spectroscopy, giving scientists their first detailed look at chemistry from another stellar neighborhood. Now 3I Atlas sits beside them in this small catalogue, making it the 3rd confirmed example. The fact that it even exists in the record is significant, because it tells us these crossings are not theoretical. They happen, but with extreme infrequency. The defining feature astronomers use to label an object interstellar is its path around the sun. In our system, normal comets and asteroids follow elliptical or circular orbits, looping back in closed curves shaped by gravity. Interstellar bodies show something different: a hyperbolic trajectory. In plain terms, that means their orbit is open, not closed. They approach, swing past the sun, and then continue outward indefinitely, never to return. A simple way to think about it is like a traveler who passes through town, buys nothing, and keeps walking, compared with a resident who moves in and settles down. That was the story with ʻOumuamua, with Borisov, and now again with 3I Atlas. Each one enters at a speed too high for the sun to capture, so their visits are brief. This makes them valuable even when data are limited, because each is material that once formed in a completely different star system. Could these be the first hints of a larger and more diverse group of cosmic samples waiting to be noticed as telescopes get sharper? That is an open question, but even the hypothesis that such visitors carry unique chemistry makes every confirmed case important. Here, the key takeaway is simple. 3I Atlas gained its importance not from detailed measurements, we actually have very few, but from the simple fact it crossed our skies at all. It stands as further proof that fragments of other systems can reach us. The challenge comes next, in the difficulty of how it was spotted and why it faded so quickly from view, leaving researchers with less information than the earlier examples. A faint discovery on the edge of detection. Why did 3I Atlas fade from telescopes almost as soon as astronomers realized it was there? Part of the answer comes from timing. It was first picked up in 2019 by the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This automated survey searches the night sky for moving points of light, mainly as a warning system for potentially dangerous asteroids. But in this case, it flagged an object already racing outward, past its closest point to the sun, and growing harder to follow with every night that passed. That late start meant scientists faced a narrow and shrinking window to gather useful data. The problems went beyond the calendar. 3I Atlas appeared faint, even compared with other interstellar candidates. Comet Borisov, seen the same year, shone brightly enough that large observatories could split its light and study individual chemical lines. Atlas offered no such luxury. By the time telescopes were turned toward it, the visitor showed up as a dim speck, easily lost against the background. Its small size added another difficulty, because less surface area means less light reflected back to Earth. Combined with high speed, that faintness ensured observers were chasing a target quickly vanishing out of reach. Astronomers measure these differences using a system called apparent magnitude. On this scale, lower numbers mean brighter objects. The Sun from Earth is about -26, while the faintest stars a human eye can see in dark skies are around magnitude 6. Modern telescopes push far beyond that, but every instrument has a limit. Atlas hovered close to the cutoff point from the moment it was recognized. Within weeks, its magnitude slipped past the threshold, leaving only darkness where the trail had been. Trying to follow such an object is like watching handwriting fade while the ink is still drying. Each day reduces clarity until nothing remains to read. For 3I Atlas, that meant astronomers managed to record its position only a handful of times. With Borisov, hundreds of measurements built a detailed map of its orbit and tail structure. In contrast, Atlas left behind only enough clues for the broad outline: speed, path, and a confirmation of interstellar origin. The difference between the two shows how much can be lost when discovery comes late. Uncertainty followed. Some researchers had hoped to search for gas or dust using spectroscopy, a method that separates light into a rainbow of wavelengths to reveal composition. Others wanted extended imaging that might show whether it developed a comet-like halo. Neither goal could be reached. The object fell below detectability before those instruments could collect information strong enough to support conclusions. The consensus today is clear. NASA confirmed 3I Atlas as interstellar, but too little light was left for any deeper examination. Its most valuable contribution remains not its details, but its very existence in the data. That leaves one final question. What can the short trail it left behind still tell us about where it came from and what kind of body it might have been? What NASA learned from the short trail? With so little time to study 3I Atlas, what pieces of evidence actually survived? The most reliable clue came from its path through the solar system. When astronomers calculated its orbit using the positions measured in those first weeks, the numbers showed something striking. Its speed as it entered was much too high for the Sun's gravity to capture. Instead of curving into a long elliptical loop, the orbit opened outward. This kind of arc is called a hyperbolic trajectory, meaning the object passed near the Sun only once before heading back into deep space. The calculations left little room for doubt. Atlas arrived from beyond our solar system and was not a long-period comet disguised as something new. Beyond that basic orbital fact, the evidence thinned quickly. Astronomers had hoped to collect spectra, which are detailed breakdowns of light spread into different wavelengths. Spectra often show fingerprints of gases like water, carbon monoxide, or cyanide in comets. These chemical markers help scientists compare material from other systems with the comets and asteroids formed around the Sun. In the case of Atlas, the small amount of light and the rapid fading of the target meant no usable spectra could be captured. That left composition as an open question. The consensus view today is that orbital mechanics are clear, but physical properties remain unknown. We can say where it came from and how it moved, but not what it was made of, or whether it showed comet-like activity, such as jets of gas. One working hypothesis is that Atlas might have resembled a comet, because most small icy bodies that roam interstellar space are expected to shed gas when warmed near a star. However, This idea cannot be tested directly with the data available. The possibility exists, but it is neither confirmed nor ruled out. Placing this in context helps. When scientists observed Borisov in 2019, they were able to measure emissions of simple molecules using spectroscopy from large telescopes. That gave them a picture of a fairly ordinary comet, but from another stellar nursery. With ATLAS, no such picture exists. What was missing was not expectation, but opportunity. The necessary time and light to run those same tests. Even so, extending the list of known interstellar travelers from 2 to 3 remains important. Each addition to the catalogue proves that these objects are not rare flukes or theoretical guesses, but real fragments of other star systems that cross our path. Even without physical details, ATLAS reinforces the fact that planetary systems form in conditions that eject material into space, and some of that material eventually drifts through ours. The key takeaway is that ATLAS matters less for what it directly showed, and more as a proof of concept for catching such visitors at all. Every confirmed case strengthens the expectation that more are out there waiting to be seen. Which raises the next challenge. How do we prepare to study the next interstellar body in depth, instead of watching it disappear before the story begins? Conclusion. Even with limited data, 3I ATLAS earned a place in the very short list of known interstellar objects. Its passage confirmed once more that material formed around distant stars can wander across our skies, even if only briefly seen. This entry into the catalogue shows that what was once theoretical is a real process shaping cosmic neighborhoods. Looking forward, next-generation surveys such as the Vera Rubin Observatory will scan the night sky with far greater sensitivity. That means future interstellar visitors may not slip away so easily. The question is simple. When the fourth one arrives, will we be ready?